Thank you so much for first inviting me, Sonia, and then for the very nice introduction. It's a great pleasure to be here. As Sonia rightfully explained, I really like this interface between fundamental work and application, being it more open science or industry, so that get to that. I mean, we all know how plants look today and how we do use energy and matter to get to chemicals, and how we would like for it to look in the next decade, such that we can ensure a sustainable transition and the carbon neutrality as soon as possible for our climate to remain under control. So this is the view that our colleagues from the Netherlands made it last year in Nature, right? So this looks quite different on the landscape as well. But for me, the question is, who will take the lead on that? And by who, I mean, will be us scientists or just industry? I mean, practical trial and error, at least from my perspective, has always been leading. There's this very nice graph from the Handbook of Heterogeneous Catalyst, and I think you can relate in every other chemistry field. Practical catalysis has always took the lead as compared to understanding. I mean, of course, this is very much based on the history of the 20th century, but I believe it still applies. So the question is, can we get ahead and really help doing the transition for a circular chemistry? And the question is then, why does trial and error still takes the lead, right? And I believe it's about, I mean, of course, money is important, but it's there the main variable is timing, right, and duration. So here it's an example based on my PhD, so it's very nice that Sonia went through that. So I was working at IFP with catalyst generation for hydrocracking. And this is in fact a commercial, a view of a commercial catalog with catalysts that are commercialized for hydrocracking. And what we know is that in fact, every of these catalysts in this catalyst catalog are out every 2 or 3 years. So as a catalyst supplier, you must put a new, deliver a new generation out in a very short time. And that is to keep you competitive, of course, in the market. So I believe that if you really want to lead the transition and that our science leads the transition to a circular, more sustainable chemistry industry, we must match the speed and the costs of trial and error, especially the speed. So what is the catalyst design problem? So I'll get a bit on the motivation to catalysis, and then it will get broader again on what we do actually regarding data and text extraction. So, but to give you the catalysis context. So in fact, you'd like to get a catalyst with a certain performance, be it typically selectivity, activity, and stability. But as you know, that's not something you can go and just find in the lab, right? So when you do the design, you design compositions, heterogeneous catalysis supports, and particle size if you have metal supported on any other kind of porous material. So that's in fact what you can play with in the lab: synthesis parameters and operating conditions. This is a multi-dimensional design space, which made things a bit more difficult, and of course the relation between performance and variables can be manipulated at the lab is quite complex and non-linear. So that's what makes also research along an iterative process. So of course, our goal here is to make this the catalyst design workflow based on the knowledge we acquire and we already have. And this means, in fact, that we need to go from data through information to knowledge. I think, I mean, being here today, I think this can be quite relatable. The point I would like really to make is that to go from fundamentals to knowledge, you need to understand what is the knowledge we have today. And in catalysis, I mean, a strong fundamental knowledge that we are having is kinetics, right? We understand reaction kinetics, we can compute reaction kinetics, we can make multi-scale models for that. So that is not the concern as of today. The concern is really on how to go from a composition, a desirable composition to a lab procedure, right? So in fact, I can even say that I would like a catalyst to the certain composition, particle size in that support. But the question is, how do I make it, right? I do need a recipe at the end. I need to say that I make a solution in this case of platinum, which would be the metal. I will need to heat up this to a certain temperature. Then I'll need to add the support, in this case, a zeolite. And for how long do I need to stir it? So we are strongly focused on, at the end of the day, deliver a recipe with model-based knowledge. So the presentation of today will be focused on that. We'll focus mainly on data and information, because to relate synthesis conditions with catalyst properties, we don't have that knowledge yet. So we must stick to data and information. In this case, we get through machine learning. Good. So this is our main motivation. And in fact, at the end, we would like to extract this data. So I will start with discussing machine learning, because we need to extract as many data as needed by our machine learning to extract information. And then I will go back to the data and how to extract the data in practice. So what we want to do with machine learning for catalyst design. I must say that this work is done here mainly in Lisbon, but also in partnership with Ghent and a colleague of Ghent that moved to KU Leuven, Florence, as well. So we started by taking the largest data set in experimental catalysis, and that's about 10,000 points, as you see at the right of this graph. And what we did was to train a random forest with this data sets, with this data set, and decrease the size such to see the effect. What you can see is that if you lower the size, there's a huge size effects on the performance in the test. So that's basically the red line. And even if you take the utmost largest data sets, which is 10,000 data points for a single chemical reaction, you don't get close to a good performance. Now, we will not satisfy with this, so we decided to make a synthetic data set, again, for a chemical reaction, a different one for the sake of variety. And in this case, we pushed it as much as we could, because we could just make up this data. So it's a simulated data set. And here you see that for this reaction, which in fact is a bit simpler, you will have decent performance already at the 10,000 data points, but in fact, this only really stabilizes at 100,000 data points. So this makes, I think, puts an order of magnitude on the amount of data we need to model catalysts, and in particular, the correlation between synthesis and properties. And so this makes this tells us that we do need to extract more data. I don't think that the data for a single lab will be enough, or that we also should focus in a single lab to generate such an amount of data for the one side. And for the other side, in practice for machine learning, we must make sure that we do the size effect between doing an exploration of the machine learning results, right? So if you are in this type of learning curve, it means that your model didn't learn all the correlation there is, and you must be very careful in interpreting this result. Saying it another way, just presenting performance metrics is not enough. You must present this learning curve as a function of data set size, because in catalysis and chemistry, we are in the low data, in the small data range. So that should be a concern. Now, we did this, and we'll come back to this result a bit later. And in fact, by extracting data. This is for a particular synthesis case. So for a type of zeolite, ZSM5, we took the largest, again, the largest data set published, which is about 116 points, which is already large for synthesis, to our perspective. And then we were able, with a algorithm that I will be discussing further, to extract 120 more points. So this made that we could double this data set to apply machine learning on it. Still, as you can see here in the result, is a performance dependence plot. You have mesopore volume, which is a key property to ensure that you can have as much metal as possible in the pores of the support. As function of NOH concentration, we use to create these pores. You see that you can roughly tell what is the trend here, but also due to the model being a random forest, you also have regions that are not very much defined. So again, the message is being very careful with the interpretation that is done to the machine learning models, but still that with 200 points and a good tuning of a model, that at least semi-quantitative results can be extracted here. I mean, you see this maximum in the mesoporous volume. This you can get back in the test data if you cross-check it. So for machine learning, that's what I would like to convey. We must be very careful about the size. We have small data in most of the fields in chemistry, but if extracting data, we can still go further. So now let's focus on the data. So we are just going through that part now. So in the future, I think we all agree. I mean, that's part of your work here. Fortunately, at NFTI for Chem, future labs should be digital labs. We won't have, I mean, there'll always be small problems in digitalization and digitization to be solved. We are on that way. That's where we all like to be. But today, that's still not the case, right? So if you look at the data, let's just particularly focus on for now, the left graph. In the left graph, there's a huge gap between fields. So if you take it from here, you see that in purple, you have the average of all scientific disciplines, and then you have biology and chemistry. What you see on the y-axis is a data set to article ratio. So basically, it's to get us an idea of how much data is being published. And here I had to multiply by, of course, you see that numbers are in orders of hundreds or tens, but I still had to multiply by thousands, right? Just to make this a bit more visible for us. This means that, in fact, average in every field, you will get only 5 data sets per 100 articles published, right? And then if you do it for biology, the ratio is about 1 to 10, but chemistry and average fields is 5 to 100. And if you go more applied engineering or chemical engineering, this goes to basically nothing. And even if you take a closer look to chemistry, here in the latest years, you'd expect that with all we are doing, things are improving, and you see quite a spike for COVID. But I mean, we are still here at these values, which are relatively low. So there's much to be done, and full digitization, or at least full availability of fair data in our papers, I think is still a long shot as of now. So let's focus on how to extract data from what is already there, right? In past data, basically, we had raw data, we did information extraction, bit more or less statistically based, and knowledge divulgation based on papers. And most of the times, data just stayed in the paper or was sent to a trash bin, which we call electronic supplementary information, right? This is kind really of a trash bin because in the sense of nothing can be extracted from that PDF file. So basically, we don't have data to work with. Even worse, it's not findable because this is a PDF file that is just hyperlinked in the paper page, so it's not searchable by a regular search engine. And also the conditions of reusability are typically not well described. Sometimes you get columns with acronyms and not even a description of what variables are or hypotheses in the calculations. So it's clear that today we don't have fair data and you cannot reuse the data that is published. So that's kind of our concern. So here we felt that the way to get data for our machine learning to learn how synthesis can impact properties and model this is really to go through the PDFs and get this data into a structured data set. So this work has been done mainly here, especially by Daniel, which is a PhD student with me and Filipa, a colleague of informatics, Katarina, and then with also collaboration with IBM. So what would we like to do? We like to extract all data in a scientific paper, store this data into a machine-readable format, and also obviously get metadata such that we get the context here. So the first question we should ask ourselves is, where is the data, right? So if you think of a paper, and for the sake of a PDF, I mean, on the catalyst or any other preparation or synthesis, basically we'll have procedures that are categorical data, if you will, and that are described in paragraphs, right? And then for the properties or even for the performance, you'll have numerical data that are mainly described or embedded in tables and graphs. So to get a comprehensive extraction of data from a paper, you should take care of all these three types of data. So what we have built is what we call PDF to data. So PDF to data basically will take a PDF classified first. So we did initial testings with OCR for character recognition, and the technology, the open technology there for reading and recognizing characters in scanned PDFs proved to be still not up to state, and we are not informaticians, so we for now exclude scanned PDFs. I think this is relevant, but this is something that dates back to prior dates back to the 20th century. So we should be concerned. We should take this historical data and make it fair. But everything that has been published after the year 2000, it's mainly text embedded PDFs. So in these text embedded PDFs, we have a text converter to go from text paragraphs in the PDF to a JSON file with the text. We have a metadata finder about the paper to also get to JSON, a reference finder, such that we can also cross-link with reference, and then we have block extractors for the tables and the graphs, which anyway will come into a CSV, a tabular format that should be that is fair. So let's start with the block extractor. So what the block extractor does is to get to recognize the layout in the paper, so you can get extract or recognize, paragraphs, titles, and captions, such that these are clearly separate from other paragraphs because it's not the same type of information that is typically written. And then you also have the figures that are recognized as well, and the tables. Then for the tables that we'll discuss first, then we need to recognize columns and rows. And this starts immediately to be a challenge because most of the times columns are not just drawn. So we need to recognize by the distance basically between characters where are the columns in a given table. And then with the table extractor, you can indeed get these kinds of structured data. So how does it really work? In fact, we tested for a relatively large data set, about 100 papers. And in the table detection, basically, we have here the metrics, precision and recall is rather high. So basically we detect most or almost all tables. For table structure, we also detect well columns and rows. And also for the captions, we can detect most of them. Where it's a bit lower is here in the accuracy. Accuracy here, it's really an overall metric in which we only consider accurate extraction when the whole table is well extracted. What happens sometimes is that one row is for some reason not extracted. Sometimes also if the resolution is not so high, this can be a bit on the recognition between the last row and the remainder of the paper. Sometimes can also see here in the header, in fact, this should be a single row, but it's detected as 2 rows because basically there's no clear lining here or draw. So that's where the accuracy problem is. So basically it's also problems you can recognize, and most of the times we do corrections by hard-coded rules. And that's it. That's what gets us to this data augmentation that I showed you earlier, and where we can get, in this case, double the data for a zeolite specific case study and allows to further do machine learning on it. So that was for the data. Now about the graphs, as I told you earlier, OCR a few years ago was still a poor open, at least was still poor as an open technology, and so graphs is something that we have basically delayed to wait for the progress to come, and now we have visual language models, right? So these are popping up more and more. We are studying on the extraction of data from graphs, and here, I mean, this is this week results. Really, we just met yesterday, and this is rather fresh. And here what you can see is results for complex figures. So this would be 5 series with captions and with chemically relevant trends. ID here stands for the correctness of detection, or good detections. What you see is that values are around 0.5 basically. So that's relatively low yet, but that's what you get with one of the best VLMs there with Quen. And what can you see? I mean, if you increase the temperature here on the left column, the temperature of the VLM, that will not change much. So going with 0 temperature will decrease the likelihood of hallucination. It will be the way to go. And then we also add a threshold on how much overlapping could be. So this is the distance between points in a graph. And here you see that when you increase the distance between points, there's a huge impact, right? So you can go from 0.5 to 0.4 in performance. So that it's important. I mean, overlapping is a main issue in extracting data points from graphs. An important point here is that we tested, in fact, 5 open VLMs, and most VLMs do skip a lot of images. By this, it means that the output of the VLM is not structured as requested in the prompt. That means that we cannot, at the end, take a table and just analyze the results as we would like. So, however, with this VLM, we are able to get to 0. But the more you increase the temperature, the more it hallucinates. So if you increase the temperature to 0.8, you get 6% of the results that are not workable, okay? Instead, you ask for a table with all the points in and a description of the caption, and sometimes the caption comes within the table, or the table has entries which are not numerical and can be categorical, okay? So that's what we have learned up to now on graph extraction with VLMs. Temperature should be, I mean, with current VLMs, at least with Quen, we should keep temperature as low as possible to prevent hallucination, and overlapping of points is critical to get the extraction right. But as you can see, we still have progress to do to come to 0.9 above accuracies that allow us to extract data without much post-processing or manual workout afterwards. And now I'd like to get to the final point of the talk, which is really text recipes, right? So what is there? What we like to do is this, right? You have a recipe that is described on this on a paper, and that with a language model, we can extract it in a standard way. So what the works that have been there for organic synthesis, that work again, in fact, by our colleagues at IBM. And here in 2020, they showed good performance to extract organic synthesis from patents with their own proprietary software. So this is a relevant work, but is with proprietary software. Then in a group of Perez Ramirez, also in Switzerland, they have been doing this now for single atom catalysis with a pre-training, in fact, in the previous data set of IBM. And in fact, our own results show that, and their own results show that without a standardization of the paragraph, so in fact, a lot of manual pre-processing, the extraction would not be that great. So what we thought is that we do need standardization, but a posteriori. So that's the first focus, was to standardize synthesis. So basically, we create a set of main actions that can be that are in fact manipulations or operations that can take in a lab, and that we believe are quite, in fact, broad or can be applied to many fields in chemistry. And we are looking forward to your feedback in saying, okay, no, you need one more action because only these are not enough. But we try for this to be elementary actions, right? So they should not overlap, and they can be combined to describe any kind of synthesis. So basically, then a synthesis can be described by a graph in which you have actions. So in this case, new mixture, for instance, add, and here you have fields in which you should, in which the data is described, solution name, volume, concentration. You change the temperature, that's an action. There's a temperature value, and so on. So this is the structured actions that we propose and that we have been using. Basically, with a clear sequential, if necessary, parallel structure and data embed. How do we see this in the overall data extraction framework? Yeah, in fact, you start by doing a prompt, right, to the LLM. So in the prompt, you immediately input the standardized action saying that I would like to get an. The LLM, a key point is that we'd like to be, or we believe that it's best to be LLM agnostic. I mean, you can always fine tune a LLM as of today, but in 2 weeks, in 2 months, OpenAI will release a new version that just completely increases performance, and in fact will and in fact your fine-tuned LLM will get out of it. We are not competing with an AI in a way, but we should take the market, or in fact in the open market, do performance line. The right for this application, and then on having a good parsing of the model response and the post-processing again to get it into this kind of structure and standardized format. So which kind of things we need to fix in the post-processing? So when you go to this original text again, and you get to this kind of structure, standardized actions, then there's still some issues with the chemical names typically. So here you add new solution, but in fact new solution doesn't mean anything, so that need to be just removed. Then sometimes you get extracted things that are multiple actions. So here you have add zeolite at 80 degrees, but in fact changing temperature is another elementary action. So we have to decouple actions that are combined together. So now we have set temperature first, and then only after you add the zeolite. And another typical issue is having complex actions. So here you would have 1 molar of chloride nitrate solution at 80 degrees for 2 hours with 20 milliliter solution per gram of zeolite. So this is quite a long ion exchange, in fact, procedure that we have built the post-processor to decouple again into the elementary actions. So post-processing is, most of the work we did was in prompt engineering to get it right, but post-processing is critical on the one hand to get the data right according to the format, and also knowing that people do describe synthesis in a concise way. We have made a dictionary of complex actions that are translatable into the elementary actions we prefer to work with, and can be also the basis for ELN or for future digitization. How does this work? In fact, if you take it for organic synthesis, the first, the state-of-the-art case study, what you see is that, again, IBM proprietary LLM in dark green will outperform. Still, our work here, it matches the open source IBM work, right? So you see the light green and the blue are both open source, the green being the work again by Voucher at IBM, and blue being ours, and we get relatively good performances. This being sequence similarity, so the order in the sequence in the procedure, right? The content and also the data as well. Then, if you take SAC synthesis, things are a bit more difficult because the work that was published by the colleagues at ETH was with pre-processing, as we discussed. So here we had to compare string similarity, so text similarity with various with 2 metrics. And what you see is that our work performs relatively well, and I would believe compound catalyst synthesis. And then if we focus on something that is more relatable to catalysis, which in this case are zeolites, you see that in blue we do outperform the other models. So again, we keep this flexibility and you keep this performance about 0.8, while others have a bit more difficult to scale or to translate to other domains in which they were not originally trained. So we believe that with this approach, and also being LLM agnostic, and with a strong post-processing based on standardized actions, this procedure can be more flexible, easier to implement, also faster to implement because there's no need for fine-tuning or training at all. So to wrap up, this was my main message for today. We would like to design catalysts to keep up with the speeds of the transition we need via models. We have fundamental models for kinetics for the reaction, so that our interest is more on synthesis and how to really get a recipe from a model, right? Such that we can design experiments and go to the lab with a knowledge-based design of experiments. As of today, the best we can do in correlating synthesis to properties is machine learning, and we are working on that, but there are so many challenges on getting the data that we focus more for now on the data. And we need to get fair data to have good machine learning, and our work has been focusing on get this fair data from the papers with focus on extracting tables, graphs, and text. I'd like to thank everyone that participated in this research. We also do other research, more applied and translating to multi-scale modeling, but this is the closed group working on data extraction and machine learning. I would like to thank you all for your attention and kind invitation.